Hello. Hi, everyone. I just want to make sure that you can hear us. So if you can hear us, please send a message into chat relay saying that you can hear us. And you won't see it on my screen, but my collaborators will be able to see this and they'll signal to me. Good. So you can hear us. Great. Well, in that case, hi, everyone. My name is Po-Shen, and I guess I'm your host because you're on our YouTube channel and in our live stream. And as you can see, I'm not quite home right now. This is not Pittsburgh, Pennsylvania. I'm in Billings, Montana. Uh, I'm actually here because in the next week, I'll be visiting some schools in Montana teaching mathematics. But we're here for a live stream that is in collaboration with a different kind of animal, a kangaroo. I guess they wouldn't be able to use those kinds of fences because the kangaroo would jump over, right? Well, Math Kangaroo is a really interesting math competition that we're very happy to be collaborating with. I love them because their questions are really, really creative. And we're particularly pleased to collaborate with them because whenever we do a live solve, they often send a person to represent Math Kangaroo. So I want to introduce her to you. I don't know if she's here, though. Actually, my partners, do you guys see her here? Is Virginia here? Virginia's not here. Well, let me just tell you, we're very happy to collaborate. Then, since she's not in this particular meeting right now, I'll just say a few words. So we're very happy that Math Kangaroo is very happy to work with us too, because well, they are actually run by a lot of very passionate people, and these people are often with backgrounds in mathematics education. Many times they're involved with universities or schools, and oftentimes they do their own other things too. In fact, I was just told that one of the state directors of one of the Math Kangaroo regions is also the creator of Number Tournament, which is an interesting math contest too. But with that, let's just go ahead and dive into the live solve. What you'll see today is going to be led by two of our extraordinary live stars who are both high school students, but you'll soon see that, man, they know everything. And with that, I'm going to turn this over to Tina and Shelly. They're going to run the rest of this show because I'm losing light also over here. So Tina and Shelly, back over to you.
Awesome. So thank you very much, Professor Lowe, and also to Math Kangaroo for this awesome live solve. Super excited to be here. Before we get started, I wanted to introduce my co-TA, Tina. She is super awesome. She is really good at math. She was a Math Counts Nationals qualifier and a two-time Amy qualifier. She was also on the AMC 8 Distinguished Honor Roll. And on top of that, she also enjoys debating, writing stories, playing games like Set, and many of her stories also feature her math experience, daily challenge included. So if everyone could say hello in the chat, give a warm welcome to Tina.
Oh, wow. Hi, everyone. Thank you for the introduction, Shelly. So I guess now I'll introduce Shelly, who is also very good at math. She is a national math counts competitor from Nevada. She was, in fact, also the state math league champion. And she's also the president of her school's math club. So she's also very popular in math. And in addition to math, she likes producing videos, piano, and teaching, which is very well suited for today's live stream.
All right, awesome. Thank you so much for that introduction, Tina. All right, so I think we're good to get started on the math. And so we'll be doing the 2018 Math Kangaroo grades 3 and 4 today, just the odd problems. And so let's just go on to our first question. Before we get started, actually, just wanted to make sure everyone got chat relay working. I see a lot of you have those messages in the chat. Make sure that in the Zoom room that you're sending a direct message to chat relay. That's the only way we can see your messages, actually. If you send it to some other person other than chat relay, only that person is going to see it. So make sure to send it to chat relay. If you're having trouble, feel free to message someone else in there and they'll help you. All right, awesome. Hello, everyone. Okay, cool. Looks like we're getting that figured out. Let's go on to our first problem, which right here. Okay, awesome. So, problem one says that Lena has 10 rubber stamps, and each of the stamps has one of the digits from 0 to 9. And she stamps the date of the kangaroo contest, which was on March 15th of 2018. And we want to know how many of the stamps that she uses. Okay, so when I see this problem, my instinct is to go from left to right and see which of the stamps that we used. So if we start from the leftmost, looks like we definitely use a 0. And it looks like sometimes the stamps are used multiple times, like the same stamp is used multiple times. Like it looks like it's used over here. And it's also used over here in the 2018. So we need to make sure that's there. So that looks like something like this right here. And the 0 is also used over here. So we'll just mark that with the same color, and then we'll count how many colors we have at the end. Okay, or actually maybe what's easier is make a tally on the side. So we have 1. And it looks like 3 is also used, and that's not used again, so that's another stamp. Okay, and then our next stamp is the 1, and that looks like it's used right here and over in the 2018. Looks like some of you guys are putting B in the chat, so it looks like a lot of you think that there's going to be 6 stamps. Okay, let's keep on moving along. And finally, there are 3 stamps left that we have not counted, but they're all different, 5, 2, and 8. So it does look like we have 3 more stamps that we used on top of the ones we've counted here. So if we total all of those stamps, it looks like we do indeed use 6 stamps. And that looks like B, which a lot of you have been saying. Of course, let's check. And it does look like B. Awesome job, everyone. That was a really strong start.
Wow, amazing explanation, Shelley. And let's move on to question 3. It says that Susan is 6 years old. Her sister is 1 year younger, and her brother is 1 year older. What is the sum of the ages of these 3 siblings? So when we look at this, we probably need to find the age of Susan's sister and her brother if we're trying to find out all of their ages. So we know that if Susan is 6 years old, her sister is 1 year younger, which means sister is going to be 5 years old. And her brother is 1 year older, which means her brother is going to be 7 years old. And with some careful addition, 6 plus 5 plus 7 is indeed 18. And C, like most of y'all are putting in. And once we check our answer, it does turn out to be C.
Awesome, awesome. That was another great question. And before we continue, we actually do have Virginia here, our Math Kangaroo representative. I believe she has a couple of words. Virginia, would you like to take on the stage?
Hello, hi everyone. I'm Virginia Wong. First of all, I apologize because I used the wrong Zoom link, so I was among the audience before. But thank you for giving me the right link to come in to say a few words to you. So I am representing Math Kangaroo today. I am their California State Director. As you know, Math Kangaroo is a very big organization. So we have like students from all over the country like participating in Math Kangaroo. And so we have like different state managers, state directors to manage the centers, to help the managers to manage their centers in different states. So I'm for California in particular, I'm focusing on Los Angeles. So I hope that most of you already knew that Math Kangaroo has been around for almost 30 years, and we have been helping over 300,000 students, range like from kindergarten to 12th grade, across the whole country to help you all build your math skills and to help you become more confident in your classroom. We create equal opportunities like for learning and education for everyone, regardless your background or circumstances. And we want to make education both accessible to you and empowering for you. I am not sure how many of you out there have already registered the upcoming 2025 Math Kangaroo competitions. If you have, awesome, and just start practicing, pay attention in this live session. And then if you still have not registered, you still have time. The deadline is December 31st for early bird discount. And after that, we still take registration, I think up to the end of January, but you will pay a little bit more. So hopefully you will act fast. If you need help or to know more about Math Kangaroo, you're welcome to contact us. You can send email to me, virginia@mathkangaroo.org. I will make sure I direct you to the right person to help you to answer your questions. Yeah, thank you very much.
Awesome. Thank you so much, Virginia, for all of that. Yes, Math Kangaroo is a very awesome competition. We're super glad to be able to solve lots of their fun questions today and also get to see so many of you join this live solve. All right, so without further ado, let's jump on to our next question. I believe we're on number 5 now. So we have Sophie the ladybug. She turns around. So which of the ladybugs below is Sophie? Okay. So this isn't showing up super well, so let me draw a little bit over that. So there's actually like a head over here, and then the antenna, and then the 6 legs. Okay, and I should draw the rest of the ladybug and these other ones. But the idea here is we need to look for something that's unique about the ladybug so that we can kind of distinguish it from all of the other ladybugs. So in this case, it looks like the head is probably the easiest to look at. So the head is facing, oh, I'm getting my directions mixed up. Let's see. Nope, wrong way. Up this way. Yes, I think. No. Up and to the left. Words work better than hand gestures. So that means if it's facing up towards the left, then the head, if Sophie turns around, must face bottom towards the right. So it looks like with option A, I know it's a little bit hard to see, so let me draw the head. But the head is facing up and towards the right, which is not what we want. So we know A is not right. B is down and to the left. So we also know we don't want B either. And then C is just to the right, which is not what we're looking for. So not C. D, however, has the head facing down and to the right. So that looks like a pretty good contender. And then with E, looks like it's also down and to the right. So this is going to be a little bit tricky. So it looks like we're going to have to look at some other distinguishing factor. It looks like a lot of you are saying either D or E. So let's see which one. Ah, I see a message in the chat that said the dots. So the dots are another distinguishing factor of the ladybug. So notice how on here, there's 3 dots on the left side, but 4 on the right. So when Sophie rotates, we know that over here, she rotates this way, the 3 dots must end up on the right side, while the 4 dots end up on the left side. And it looks like that is the case in option E. So I think a lot of you are saying option E, so let's go with that. And of course, we have to check, is it option E? Oh, not there. Oh, it's D. Okay, interesting. Let's go back and see why that is. So let's see. Let's see, Tina, did you also get E for this one?
For this one, honestly, yeah, let's read this question statement again. She says she turns around and asks which of the ladybugs below is Sophie. And I also don't think it could be D because Sophie's head is turned differently in the original picture and in D, but the dot placement is still the same, while E actually, well, if we look at E, your explanation is correct. And if you imagine it, and if I like cut out the Sophie picture and flip it around, it would look like E.
Yeah, I think so. I think there might have been an error in the slides. I do agree. I think it's also E, like a lot of you have been saying. So yeah, I think it is indeed E. So awesome job, everyone in the chat. Let's keep on going.
All right, hopefully this will be slightly less confusing. And first, let me zoom in on this a little bit so it's easier to see both the question statement and the diagram. Yeah. Hopefully this is easier for y'all to see. And it reads, on her first turn, Diana scored 12 points total with 3 arrows. And on her second turn, she scored 15 points. How many points did she score on her third turn? So if we look at the diagram, the target labeled 12 points is her first turn. The target labeled 15 points is her second turn. And the third target is what we don't know and what we're trying to find out. So we know that she shoots 3 arrows in each of these. And let me use a light blue arrow for the lighter region and a dark blue arrow that looks like purple. Okay, here's a dark blue for the darker region. If we look at the first diagram, there are 3 arrows in this light blue region, and all arrows landing in the light blue region score the same, which means if there's 12 points total, then each light blue landing arrow is going to score 4 points. And if we look at the second diagram, we know that there are 2 light blue arrows that score 4 points. But there's also an arrow that lands in the dark blue section. The arrow that lands in the dark blue section is going to score some amount of points that add up to 15. If we subtract the sums of the first 2 arrows from 15, we would get 15 minus 4, which is 7. So each arrow landing in the dark blue section is going to be 7 points. And on her third try, Diana gets really accurate. So all of her arrows land in the dark blue section. They each score 7 points, and that adds up to 21. And it seems like a lot of you are getting this in the chat too. So let's see if we're right. And the answer is indeed 21.
Awesome. This is a really nice puzzle. It's ultimately boils down to algebra, which I think is super fun. It's nice to find out, how many points it is on the inside and then being able to determine that. And that's what's nice about these Math Kangaroo problems is that they all are a puzzle, but kind of boiled down to the fundamentals. Awesome. Okay, so let's go on to the next question. So Roberto makes designs using tiles that look like this. How many of the 5 designs is it possible to make? Okay, interesting. So I think maybe what's good is to just, again, go from left to right. So seeing if it is indeed possible. So with our first option, a possible tiling, and it seems like there's probably multiple ways of doing this, but if we want to check a possible tiling is something like this. So with one star looking thing, I think that's like a star, one star looking thing and one that's blank. So this is indeed a possible configuration. So let's look at our second one. So our second one, we have something like this, and then things start to get a little bit tricky. So notice how these 2 stars over here are kind of like competing for this square. So that might actually cause issues later. But let's keep on moving. Maybe one of them takes this one over here. The other one takes this one. And then we are outlining here, and uh-oh, looks like we have a problem because there are 3 of the stars surrounding one blank tile, which isn't good because we need to have a domino such that we have 1 star and 1 blank. The reason why actually this tiling is impossible is because notice the number of stars compared to blank tiles. So if we even want a chance to make a possible configuration, we need to have an equal number of stars to blank tiles. If we have an uneven amount, then we cannot pair these to each other. And notice over here, it looks like we have 8 stars, but we do not have 8 of the blank tiles. In fact, it looks like we have 6. So we're not going to be able to pair each blank tile to each star tile. So this second one is actually impossible. So we can cross that out. And then over here, we can do that. So if we tile it like this configuration is also possible. So we're good. And then let's take a look at our fourth. So our fourth looks like it's possible as well. So if we do something like this here, and then these 3 down there also form the domino, so we're good. And then finally, with the one at the rightmost, looks like that is also possible if we have something like a cycle. So like this, this, and that. So it looks like the only one that wasn't possible was this second one. All the other ones work. So it looks like our answer choice should be D, the 4 different designs. And of course, let's check. And yeah, looks like we do get D, 4 of them. So awesome job, everyone. And let's keep on moving right along.
Sweet. And before we move on to question 11, I think a lot of people are contesting one of the designs. And a lot of you are saying that there is a blank in the middle of one of them, which means it cannot work. Let's look at a clean diagram. I think, yes, you are right that there is a blank in the middle, but however, we do not need to fill in the blank. We simply need to put the 4 tiles around this. You rotate the tiles, you put them next to one another, and it forms a square with a hole in the middle. So it is possible to make this last formation with 4 tiles. Yeah,
Oh,
I think it's a little tricky.
I think the issue here is it shows the middle tile as the same as the other ones because I'm noticing the colors look different on our end, but it doesn't look different from your guys' end probably. Because I think for you guys, these both look clear, right? So I think maybe we should have made this more clear at the start, is that the blank tile is actually slightly shaded in the diagram. Yeah, the middle is blank. We know it doesn't really look that way, so we should have made that clear. But actually, this diagram on the very right, this one is one of the blank tiles. This one's another one. This one's another one, and this one is another one. And the center square is actually like there is nothing there. There's nothing that we have to fill. But you guys are correct in saying that if this was also one of the blank tiles, like if it looks something like this, then the configuration would not be possible, right? Because going back to the idea that we need to pair a star tile with a blank tile, we see that there's going to be 5 blank tiles and 4 star tiles, so it's impossible to match up. So if it was something like this, then totally agree that that's impossible. However, we did have our problem with nothing in the middle. So yes, good job on pointing that out, you guys.
Yeah.
Yeah, awesome.
Oh, wow. Thanks for the clarification, Shelley. So now that we have this cleared out of the way, we're in a more general consensus that the answer is D. Let's move on to number 11. It's also a geometry puzzle. Tom cuts 2 kinds of shapes out of grid paper shown below. What is the smallest number of shapes that Tom needs in order to exactly cover the boat in the picture? It seems like he's trying to make a boat. And something I noticed with this about his boat is that there are these places that stick out a little. And it seems like we need the trapezoids to cover those areas. So I'm going to outline a trapezoid in pink and first put some trapezoids to cover the edges that stick out diagonally on both sides. So let's see. The trapezoid has a smaller base of 2, a larger base of 6. So we can put one of the trapezoids like this. And then we do the same with the other side. And the nice thing is we can actually fit a trapezoid in the middle. So right now we have 1, 2, and 3 trapezoids. Then we need to figure out what to do with the squares. Let's make these squares yellow. The squares are 2 by 2 squares. So I can fit the first one here, the second one here, and the third one here. So 3 squares plus 3 trapezoids ultimately equals 6 total shapes. And it seems like most of y'all in the chat are also agreeing that the answer is B.
Hey, awesome. Good job, you guys. You guys are really participating in the chat, so definitely keep that up. And let's move on to the next problem, which looks like number 13. Okay, so number 13 says that Peter Rabbit has 20 carrots. She eats 2 carrots every day. She ate the 12th carrot on Wednesday, and so on which day did she start eating the carrots? Okay, so with these kinds of problems, I usually like writing out the days of the week. So I'll represent Sunday with an S. So S, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So just to have that to keep everything straight. And we are given that she ate the 12th carrot on Wednesday. So on Wednesday, the 12th carrot was eaten. We also know that she eats 2 carrots every day. So we know that on the first day at least, she would have eaten the first and second carrot. The second day, she would have eaten the third and fourth. And the third day, she would have eaten the fifth and sixth. And so it seems like this is going to be the sixth day. So because notice how on when she eats like an even number of carrots each time, we're kind of skipping by 2. So 2, 4, 6, 8, 10 to 12. So on Tuesday, that means we can say that PETA ate the 10th carrot, right? Because we know that PETA ate the 11th on Wednesday, so that already adds up to 2 carrots. So on Tuesday must have been the 9th and 10th. And if we keep moving along, on Monday she ate the 8th, Sunday she ate the 6th, Saturday she ate the 4th, and then on Friday she ate the 2nd. So does that mean that she ate the 0th carrot on Thursday? Well, not quite, right? Because on Thursday we don't even have any of the carrots. We actually start on Friday because we're given that she eats 2 carrots every day. So in addition to eating the second carrot on Friday, we also know that PETA must have eaten the first carrot on Friday also, because that would amount to the 2 carrots. So that means overall, Friday must have been the day that she started eating the carrots, which seems to line up with what you guys are saying. So let's check, of course, with Friday. And it indeed is Friday. So awesome job, everyone.
All right, excellent work, everyone. Let's move on to number 15. Oh, wow, this is a pretty hefty word problem. Let's zoom in so we can read the words better. It says, there are 8 flowers on a rose bush. Some butterflies and some dragonflies are sitting on the flowers. There's no more than one insect on each flower. More than half of the flowers have an insect on them. And the number of butterflies on the flowers is twice the number of dragonflies on the flowers. How many butterflies are sitting on the flowers? Oh, this is quite a riddle. And as T.A. Michael said, lots of words means we have to make sure we actually understand this problem. So we know that there are 8 flowers on the bush, and I'm going to pretend that these flowers are yellow. Is there a diagram drawing place after this? Oops. So let's draw the 8 flowers. 3. And once we have 8 flowers here, next it says that there are butterflies and dragonflies on the flowers. There's no more than one insect on each flower. So there is either one butterfly on a flower or one dragonfly. So there are a certain amount of red butterflies and green dragonflies. It says more than half of the flowers have an insect on them. So we know that at least 4 of the flowers will have either butterfly or dragonfly. And finally, it says the number of butterflies on the flowers is twice the number of dragonflies, which means for every dragonfly we put on the flower, there's going to be 2 butterflies on other flowers that correspond to this. And to make this easier to understand, if we put a dragonfly on the first flower, that means there are going to be 2 butterflies. You don't have to be sitting exactly next to this dragonfly, but there are 2 butterflies for that dragonfly. Next, we can still fit in another dragonfly because we have not filled in half of the flowers yet. And that means we need to put 2 more butterflies on other flowers. And I think they've turned a different shade of red. And finally, we have 2 flowers left. if we put a dragonfly down here, there's only enough space for one more butterfly, meaning there are not three dragonflies. Because if there were three dragonflies, we would need another flower for that second butterfly, which means only six flowers are going to have insects on them. And if we count, there are four butterflies total here, which means the answer is C. And it seems like most of the chat agrees with me. So I think we're right.
Right, excellent. Okay, let's go on to our next question. Actually, we've hit past the halfway milestone, so keep on going strong here. And let's take a look at number 17. Okay, so the rooms in Kanga's house are numbered. Baby Roo, that's a very nice name. Baby Roo enters the main door and passes through some rooms and leaves the house. The numbers on the rooms that he visits are always increasing, so through which door does he leave the house? Okay, so this one looks like it would probably take some trial and error. So let's just start with this number one here. So it looks like there's multiple paths that we can go from number one. We can either go to 3, 5, 9, 10, or 2. So just for giggles, we just want to keep it systematic. Let's start by going to the left first. So if we enter through 1, we go through 3, and that's totally fine. That's increasing. And of course, we can't go back to 1 because, I mean, that isn't very productive, first of all, but also 1 is less than 3. So we know we can go to 5, 6, or 4. All of those are greater than 3, so we can really choose any of them. So maybe we can go with 4. That's fine. Then we go to 6. That's actually when we run into issues. We're not allowed to go diagonal here, so we're only allowed to go through the opening, so the slits here. So once we hit 6, though, we actually run into an issue because we're forced to go to 5, and that's less than 6, so that's bad. We know, therefore, we cannot go this way. And so if we backtrack, maybe we can go down 5 instead. Going down 5 is fine. It looks like we can either go to 6 or the 9, but if we can't go to this 6 here, because that's the issue we ran into earlier, so we can go through this 6, and it looks like from here, we're forced to go to the 7, because otherwise we'd have to go to one of these 5s. So we can go to 7. From here, we can really go in any direction, except maybe going back to 9 isn't very helpful, because we could have also done that from the start. So we could, maybe let's just choose this 8 here. And after this 8, we're forced to go to 9, because we can't go to 5 or 6. And, oh, some of you can't see this clearly. Okay, we'll have to enlarge in this later. But after 9, we're going to go back down to 10, and it looks like we're able to exit through D, which is what a lot of you are saying. All right, awesome. And let's see, this is a larger diagram if you guys were looking for that. So right here, I think to outline the path that we went through. Okay, let's see, hopefully this is big enough. So to outline the path that we went through, I think there's multiple ways that we could have done this, but this was one of the possible ways to go through the house. Maybe I shouldn't do orange, maybe we'll do yellow. So this was one of the possible ways, and that led us to go through D, which a lot of you are saying. All right, awesome. And it indeed is D. Good job, everyone.
Wow, amazing. This was a really fun problem. And number 19 also looks pretty fun. It says a band shown in the drawing can be fastened in 5 ways. How much longer is the band fastened in one hole than the band fastened in all 5 holes? So let's see. This kind of reminds me of some of the bracelets I would get in school events where I'd have to put the holes into the fastener's buttons, I think, and I can adjust how tight it is. So this is what it shows when the band is fastened in one hole. So in between the holes, there is 2 centimeters. So if we fasten one hole, the length of the band would decrease by, if we fasten it in one hole, then it would be this going in here. And if we fastened it in all 5 of the holes, then these 4 places would be covered up. And at this point, we're having a little disagreement in the chat about what the answer should be. So let's think about this a little. Let's see, is there a diagram down here to help us out? Oh, sweet. We have a diagram. If we just put the first hole into the first fastener, this is like the default setting. And at this point, we don't really care about what the length of the band is. But once we start putting the buttons into the fasteners, like the second one in here, the length of the band would decrease from the default length by 2 centimeters, because these 2 centimeters between these 2 fasteners will overlap these 2 centimeters. So it will ultimately lose 2 centimeters. Yeah. And someone else said with every hole, circumference decreases by 4. Does it decrease by 2 or by 4? I still think it will decrease by 2, because it's not like you're getting rid of both of these lengths. It's just that this part is going to overlap this part. So yeah, I think Stephanie's saying it is 2 from this side onto that side. So we know that the length decreases by 2 centimeters every time we fasten a new hole. And in between these 5 holes, there are going to be 4 gaps of length 2 centimeters. There's this one, this one, this one, and this one. And 2 times 4 is giving us 8. Let's see, is 8 on here? 8 is indeed on here, is answer choice B. It seems like some of y'all were confused about this, and hopefully my explanation cleared this up. Let's check the answer just to be sure, and it is indeed 8 centimeters. Excellent work, everyone. Yeah, hopefully you understood. Mhm.
Yeah, and if it's still a little bit confusing, I'd encourage you to actually take out a slip of paper and make this. I actually think if you were in the contest and they allow you to take a slip of paper and kind of cut it out, you can actually make this exact diagram. You can like fold a thin strip and then kind of tear it off and then poke through 5 holes on each side and then try it on your own. You can try fastening or quote unquote fastening the band on your own, and you'll see that I think the trickiest concept to grasp is how much the band decreases for every hole that you fasten it by. But as Tina was saying, every time you fasten the hole, it's actually by 2 centimeters, not 4, because this section over here overlaps with the other section over here. So it's still going to be 2 centimeters. And if that's still not clear, definitely try doing the strip of paper. I think that'll really help. Awesome. Okay. Cool. Yes, that 2 centimeters goes on under the other side. That's a good way of putting it. Okay. Cool, cool. Let's go on to number 21. Ooh, okay. This is a big diagram. Hopefully you guys can see this. Let us know if you can't. And so let's see. This problem says that the hexagonal stained glass tile is flipped. One of the flips is shown. Looks like that's done right here. And so what does the stained glass tile look like on the far right? Okay, I can't see it clearly. Hopefully there is. Okay, this is a larger diagram. Let us know if it's still unclear. Can make it a bit bigger. Okay, and so let's go back to the question really quick. Okay, what does it look like on the far right? Okay, so we want to know all the way to the right. I'm realizing you can't see my hand if I put it behind there. So I think what they're asking for is what this tile outlined in orange looks like. Okay, so let's see, we've got mixed opinions. So let's take a look here. Well, we need to know somehow how each of the figures or how each of the creatures are oriented in relation to each other. So notice how on the edge of where the glass tile is flipped, the creature is exactly the same. So see how this creature right here, the ladybug, is flipped and it's on this connecting side in the middle. So I'll highlight that connecting side in yellow. And so notice how over here too, if we look at the dolphin on the right side, it's going to be slightly above where my finger is pointing. That means the dolphin, when you flip it, must be over here somewhere, right? So we know the dolphin is here. Please forgive my art skills. This is going to be the best dolphin I can do. It's like something like a curved thing. I know you guys could probably do better art things than me. But for now, hopefully this shall suffice. And so in relation to that, think of it as a mirror. So we can think of it as like this ant over here must flip over to this tile right here. The cat must flip over here. And then therefore, the butterfly must flip to this tile over here. We can think of it as going one by one. Another way we could think about this is how each of the individual triangular tiles are distant from the folding line. So for example, the dolphin is immediately next to the fold line. So when it reflects, it should still be right next to that fold line. Same thing with the ant, or something similar with the ant, right? So it is one away from the flip line. We know it must remain on that same side as the flip line. So when it goes over, we know it must go to, I'm going to highlight it in, let's see, dark purple this time. We know that it must head to this tile because it is one away from the fold line and it still is on the same side. So it's still on the upper right-hand side of that fold line. So if we use a similar logic for the other creatures, then we can say the butterfly ends there. Once the butterfly ends there, it might be easier to see the next flip. So yeah, exactly as someone said in the chat, look at the butterfly. This is a good point because if this is one of the fold lines and the butterfly ends up here, that means the butterfly, after getting flipped, must end up over there. So look at the top right hexagon. It must be on the bottom left side. And if we look at our answer choices, there's actually only one tile that satisfies this, and it looks like it's going to be this one right here. This tile is the only case where we have the butterfly on the bottom left. And it seems like a lot of you are super excited about this, that it is indeed B. And I see a lot of you guys used a similar strategy of focusing on one of the animals and then seeing how they are oriented through each flip, which I think is a really good strategy. So let's go with B. And looks like we do get B. So awesome job, everyone.
Sweet. Yeah, I also agree that there are multiple different ways to solve this problem. We can, like Shelly, figure out the orientations of different animals as we flip. Or once we look at the answer choices and realize that all of the answer choices are an exact rotation of each other, meaning that the animals in the answer choices are all in different spots, you can track your favorite animal. And some of y'all are also wondering if the brown thing was a squirrel. Honestly, it looks like a dog to me. I can also see the squirrel, but the dog is upside down. So hopefully you can also see the dog. Yeah. And let's see what question 23 is about. This is, in fact, our final question. So this is super exciting. It reads, Leon wants to write the numbers from 1 to 7 in the grid shown. Two consecutive numbers cannot be written in two neighboring cells. Neighboring cells are those that meet at an edge or at a corner. What numbers can he write in this cell marked with a question mark? Oh, I think this is tough. I honestly don't know the answer immediately looking at this question, but I think we can try some cases. So when it says two consecutive numbers cannot be in the two neighboring cells, that's a good question, Lydia. Let's write out the numbers 1 through 7 to organize our thoughts down here. Two consecutive numbers mean they're right next to each other on the number line. So 1 is consecutive to 2. 2 is also consecutive to 1. And 2 is consecutive to 3. But 1 and 3 are not consecutive because you have to jump over 2 if you want to get from 1 to 3. Yeah, Jay, that's a very good explanation. Consecutive is like going from 1 to 2 or 6 to 7. But that also means we cannot put 1 and 2 next to each other on the grid. Putting 1 and 2 next to each other is not going to be good. And something else that can help us is looking at the answer choices. What numbers can he write? There's either all 7 numbers, all of the odd numbers, all of the even numbers, only the number 4, or only the numbers 1 and 7. So I think a good way to test is by putting D says only the number 4. So if we put 4 in here and nothing works out, then we know that answer D is not correct. So let's see. If we put the number 4 in here, we'll need to find 3 numbers that are not consecutive to 4. And we can put some close ones like 1, 2, and 6. We can put 7 in here because it's far away from 1. We can try putting 5 next to 6 and 3. So 4 definitely works. And let's try the other extremes of 1 and 7. I honestly don't think odd and even will, and we also know that all of the odd numbers is not the answer because 4 worked in here. So now let's put 1 and 7 in here to try to knock out either claim C or claim E. So if we put 1 in here, there's actually a lot of numbers that are not close to 1. We can put 3, 4, and 5, and then we would leave off 2, 7, and 6. So 1 also works, which means all of the even numbers is also gone, and only the number 4 is also gone. So now I think it's time to test a number that isn't 7, because if 7 works, we confirm E. But if 2 works, then we know that the only answer choice is A. So let's scratch out C and D again, and let's plug number 2 in here. Let's put 4, 5, and 6 away from 2. 7 is not consecutive to 4, 1 is not consecutive to 5, and 3 is not consecutive to 6, meaning that 2 works, which means numbers other than 1 and 7 work. We could have also eliminated E when we tested out number 4, which means the answer choice is A. It would take a lot of time to test out all of the numbers from 1 to 7, but using our answer choices, we can quickly eliminate most of them.
Cool. And let's see. Let's check. Should we check this?
We should.
Okay. Oh, hmm.
Oh, it
Interesting.
says cannot
Only 1 or 7. Oh, okay. Interesting.
be written.
Oh, wait, I think one of the things is it also can't share a corner. So like it can't do these two cells, but it also can't share a corner. So if we had something like what's an example? Like if we had something like 3, oh, this is not showing up. Like if 3 was here and then 2 was up in that corner there, that also wouldn't work because they share a corner. So I think that complicates things a little bit.
Wait, that does make sense. So it's important to read questions before trying them. But I think we have a better understanding of this question now. So it will definitely help us if we tried again. Let's clear off all of the markings off of the board. And I think there's a diagram down here. Well, nope, there's no diagram. So let's keep working with this. We know that they cannot meet at an edge or a corner. So if we look at the center square, we know that it cannot be consecutive to this number, this number, this number, this number, or this number, which means the center square cannot be consecutive to 1, 2, 3, 4, 5 numbers. Oh, wow, that is a lot of numbers. And if we choose a random number, let's start with 4 again. 4 is consecutive to 3 and 5, meaning it is not consecutive to 1, 2, 6, or 7. And 1, 2, 6, and 7, that's only 4 numbers, which means 4 cannot go in here. So D is wrong again. And if we look at the other numbers, like 2, 3, 5, and 6, they're all in the middle. They're not edge cases, meaning they're consecutive to two numbers. And there's six numbers that are not the number we choose. So they're not consecutive to four numbers. But what we want is a number not consecutive to five different numbers. So that is some good logic behind why 1 and 7 would work. But we also need to test it out. So if we plug 1 and 7 back into this diagram, let's try 1 in here, 3, 4, 5, 6, and 7 could work. And we could manage to fit all of these numbers around. Wait, oh, right, I forgot that. Let's switch the 2 and the 6, and this can work. And I think if we flip out 1 and 7, this also works. So the answer choice is E. Yeah, all of us are having our minds blown. And I'm so glad this makes a lot of sense. It was pretty challenging.
Yeah, for sure. I also had trouble with this one at first because I was like, wait, because all of them can work, right? Because I also did something similar with like ruling out each of the answer choices. I think the thing mainly to keep in mind is, as Tina was saying, 1 and 7 are like the edge cases. They only have one consecutive number next to it. And that works out here because whatever number's in the middle here is forced to be or forced to have all of the other numbers, other five values around it not be consecutive to it. So that leaves only one space or one value that can be consecutive to that number. So that means if the number, like say 4, had two consecutive values, in this case it would be 3 and 5, then it'd be bad because we only have one slot for it. So hopefully that clarifies it a little bit. And that is actually all we have for today. We've done all of the odd numbered problems, so we are done. Thank you guys very much for staying all this time. It was really awesome to see the chat being so active and you guys submitting all your thoughts here. And we hope to see you in a future session. Right.
All right, yeah. Thank you everyone for coming. And seems like y'all want more math. Don't worry, Professor Lowe has more live streams coming up, and you could always participate in more Math Kangaroos to get more of these amazing problems. Yeah, yeah,
Thank you, everyone. We hope
yeah.
to see you
Thank
in a
you.
future session. Bye.